All right, let's take a look at section 6.3 before we go over yesterday's questions. So turn to page 421. Actually, turn to page 427. All right, in yesterday's section, the exponential growth model is derived from the fact that the rate of change of a variable y is proportional to the value of y. You observe that the differential equation dy dt equals ky has the general solution y equals c e to the kt. Exponential growth is unlimited in theory. But when describing a population, there often exists some upper limit L past which growth cannot occur. This upper limit is called the carrying capacity, which is the maximum population, y of t, function of y as the population is a function of time, that can be sustained or supported as time increases. A model that is often used for this type of growth is the logistic differential equation. dy dt equals k times y times the quantity 1 minus y divided by L. That is the logistic differential equation, where k and L are positive constants. A population that satisfies this equation does not grow without bound, but approaches the carrying capacity L as time increases. And so then the graph of that would look like so. Okay? Can't grow forever, so it has some limiting horizontal line as the limit. It has a horizontal asymptote. Okay? Now, let me show you how they derive that general solution. So it says solve the logistic differential equation dy dt equals ky times the quantity 1 minus y over L. So we begin by separating the variables. So let's see, what all did they do there? They had to multiply both sides by dt. Then they got rid of that y by multiplying both sides by 1 over y. And then they got rid of the 1 minus y over L by multiplying both sides by 1 over 1 minus y over L. And they end up with this. Okay? Then you integrate both sides. So that's what they're doing right here. And then the one on the right, that one's easy to solve. Okay? It's just the integral of a constant dt. That one's easy. The one on the left, though, requires a little work. But it's not quite as bad as you might think at first, because if you rewrite this into, look what they did there. Okay? Because this is all screwy looking, but they and I don't want to go through the steps. They took the steps to go backwards and separate that into two separate fractions. Okay? So, using partial fractions, making it into partial fractions that are portions of the whole. All right? Then, they've turned it in. We can do that, natural log. We can do that if we let u equal L minus y, and then du would equal negative dy, and so negative du equals dy, so we get a negative there. Okay? Integrated the other side and got a plus c. Use your logarithm properties over here to make that the logarithm of one expression. Then they exponentiated both sides. And then once you exponentiate both sides, once you have e to those two things, you do what we've been doing, right? Make it e to the negative k times e to the negative c. and e to the negative c will in fact be a constant. They called it b. Didn't see that coming, did you? Call it b. And then solve that thing for y. They skipped about, I don't know, half a dozen steps to solve that for y. Okay? And then we end up with that. What's the point of all this? Fine. Can conclude that all solutions of the logistic differential equation are of the general form ch. Okay? All right. Now, I'm kind of glad the book worked that out for us. I'm not real sure that if we'd have started there, we would have ended up there. Are you? No, I'm pretty sure we wouldn't have. Okay? So they worked that out for us. I'll hold off on that. So, questions from yesterday? (14) and 28. All right, on 14. Let's see. The rate of, so it says write and solve the differential equation that models the verbal statement. The rate of change of y with respect to x. The rate of change of y with respect to x is dy dx. Varies jointly as x and L minus y. So that was the one that I didn't remember either. We had to look that up. So varies jointly as, if it was varies jointly as x and y, it'd be a constant times x times y. So whatever it's varying jointly with, multiply those together. So x and L minus y, and then the varies jointly means that there's another constant times it. So I called it k. Okay? So, I didn't remember it either, so I had to look it up. So dy dx equals k times x times L minus y. So I can definitely see how you might have a hard time writing that equation. But once we have it, then let's be able to do the rest of it. We've written the differential equation. Now let's solve it. Let's separate the variables. So I need to multiply both sides by dx. I need to, so that gives me an x and a dx on the right. Then I need to get rid of the L minus y on the right, don't I? So multiply by 1 over L minus y. And I think that's it, isn't it? So the dx is divided out on the left. The L minus y is divided out on the right. So we get 1 over L minus y dy on the left. We get kx dx on the right. In theory, at least, we can solve this. So we're sitting here. Take the integral of each side. And then on the right side, I went ahead and factored that k out in front. On the left side, that's going to be the natural log, but I've got to get the u work out. And really the thing to worry about is the sign, right? Because when you take the derivative of L minus y, you get a negative dy. So let u equal L minus y. So du is negative 1 dy. Let's make that negative du equals dy. So then let's do our substitution. The integral is the integral. 1 is 1. L minus y becomes u. dy becomes negative du. So we've rewritten it. We can solve that. And we already know how to do the one on the right side. So far, so good? All right. So when we integrate 1 over u du, I get the natural log of the absolute value of u. And at this point, there's still a negative sign there. And there's not one over here. And then on the right, keep that constant, then take the integral of x dx. So that'll be 1/2 x squared. Don't forget plus c. Okay? And then what I did is I went ahead at that point and multiplied both sides by -1, that original C got also multiplied by -1. Why didn't I put a negative right there? Just because it got multiplied by -1 doesn't mean it's now negative. If it was negative to start with, so it doesn't matter, does it? We still don't know what that constant is. Writing minus C1 and writing plus C1 doesn't matter. We don't know what the constant is. All right? Put the L minus Y back in for U. Exponentiate both sides so that I can get that Y out of the exponent. On the right side, we've got e to the, and then two things added together. So make it e to the first one times e to the second one. E to the C1 is itself a constant. And then I've got that negative y, since it was L minus y. Subtract L from both sides, it's still a negative y. Multiply everything by a -1. At that point, instead of calling that C3, I'm just calling it C plus L at the end. Does that help for 14? Okay. You know what's kind of scary? Once we have that one written, that one didn't seem all that difficult. Did it? I think we've done enough of these. I hope we're getting pretty good at them. And 28. All right, on 28, what's going on here? It says find the exponential function y equals c e to the kt that passes through the two given points. And our two given points are 3, 1/2 and 4, 5. So at the point 3, 1/2, put in a 3 for t, a 1/2 for y, and wouldn't it be awesome if either the c or the k went away and we solved for the other one? That'd be awesome. Didn't happen. Okay, so I tried the other point. Maybe it'll happen when I do the 4, 5. So I put in 4 for t, 5 for y, and hopefully either the c or the k disappears by magic and I solve for the one that's left. Doesn't happen. But what I now have is I have a system of two equations with two variables. In theory, I can solve that. So let's see if I can. And there's a lot of different ways to go about solving a system of equations. You've learned a lot of them. So here's what I did. Okay? If I take, I'm just going to call this equation 1. If I take equation 1 and I multiply both sides by 10, hopefully you're thinking, why would you do that? I'll multiply both sides by 10. 10 times 1/2 is 5. C e to the 3k times 10 is 10 c e to the 3k. So this is still equation 1. It's just both sides got multiplied by 10. Now look, equation 2 is 5 equals c e to the 4k. So look, I chose a rather unorthodox method of solving this system of equations. If 5 equals 10 c e to the 3k, and 5 also equals c e to the 4k, don't those two things that both equal 5 have to equal each other? Transitive property. Okay? So that means that 10 c e to the 3k equals c e to the 4k. And I have a brand new equation, but it works out really nice when you divide both sides by c. So the c goes away. Divide both sides by c, and you get 10 e to the 3k equals e to the 4k. All right? So, are a bunch of problems going to work out just like this? No. This one, though? Yeah. So is this a pretty good way to work it? Mm-hmm. All right. At this point, let's divide both sides by e to the 3k, because I don't want a k on each side of my equation. If I divide both sides by e to the 3k, on the left side, e to the 3k divided by e to the 3k is 1. 10 times 1 is 10. And on the right side, when you divide factors with the same base, you subtract the exponents. So e to the 4k divided by e to the 3k is e to the 4k minus 3k, so e to the k. So I'm real close to knowing what k equals. Take the natural log of both. The natural log of e to the k is just k, and now I know what k equals. It's the natural log of 10. So we have almost a particular solution at this point. We can rewrite our general solution, y equals c e to the kt, as y equals c e to the natural log of 10 t. For the next part, just take one of the points, put the t coordinate in for t, the y coordinate in for y, and solve it for c. I didn't want to have to deal with the 1/2, so I chose 4 or 5. So I put 4 in for t, 5 in for y. That gives me this, and then you can follow the rest of it out, solve it for c. Okay? And now we have the particular solution. All right, what else would you like to go over from yesterday? 47. Right on this one, it says complete the table for a savings account in which interest is compounded continuously. So they're telling us to use the y equals c e to the kt, which I'm going to convert to a equals p e to the rt, just because that way we know what all those constants stand for. Okay? And on 47, our initial investment is $500. So P is 500, and the time or the amount after 10 years is $1,292.85. So here's what I did first. I've got A equals P e to the RT. When they tell me what P is, I can make a little bit of a more particular solution. Okay, so A equals 500 e to the RT. And then if it takes it 10 years, no, if they tell me the amount after 10 years, they're telling me what A equals when T equals 10. So they're telling me the point 10, 1,292.85. So I can solve for R by putting 10 in for T and $1,292.85 in for A, which gives me that. And then it takes a few steps, but I get to solve it for R. So, you guys follow me solving it for R? All right. Once I've got that, I can answer their questions because now I have the particular solution. Because A equals 500 e to the 0.095 t. So if they tell me t, I can figure out A. If they tell me A, I can figure out t. So they ask us for the time to double. Well, if you started with 500, once it's doubled, it's 1,000. So 1,000 equals 500 e to the 0.095 t. I divided both sides by 500 to get that. Natural log of both sides. Divide by 0.095. That's how many years it takes. Okay? Which one? 16. There's 16. Do I need to do any explaining for 16? All right. Let's see. So to get that, you just try to follow the little slopes. All right. So we've got dy dx equals xy. So let's separate the variables. Let's multiply both sides by dx. But then on the right, I've got x, y dx. Don't want the y, so let's multiply both sides by 1 over y. And I think I've got it. So on the left, the dx is divided out. And on the right, the y and the 1 over y divides out. So I've got 1 over y dy on the left, and I've got x dx on the right. And let's integrate both sides. So you're able to follow me to that red check mark there? All right, now that I've separated the variables, the integral of 1 over y dy is the natural log of the absolute value of y. The integral of x is 1/2 x squared plus c. Called it C1 because I've done enough of these to know that I'm going to have a different C at the end. Okay. And by the way, if you just call it C, and then you get down to this step and realize you want to make another C, all you got to do is go back and put little ones there. Okay. So it's not like if you don't know it's coming that you're sunk. All right. So exponentiate both sides. Use the property that says when you multiply factors with the same base, you add the exponents backwards to get that. E to the C1 is itself a constant that I'm calling C, and this is my general solution. We able to get down to the general solution? Any questions getting to the general solution? All right. Then at the point 0, 1/2, because they tell us the point 0, 1/2, put in a 0 for x and a 1/2 for y. That allows us to solve for c. E to the 0 is 1, so c equals 1/2. And there we go. Does that take care of 16? Any others? 10? All right, on number 10. It says to solve the differential equation. So we've got xy plus y prime equals 100x. All right, so I subtracted xy from both sides, and at the same time, I rewrote that y prime as a dy dx. That gets us this far. Okay. If I multiply both sides by dx at this point, and the dx ends up over here, I've still got a y there. Okay. So I need to factor an x out. Because that way, if I multiply both sides by 1 over 100 minus y, I'll have just x on the right, I'll have the y terms on the left, and I'll be in business. So I factored that, and then the next stage is multiply both sides by dx, multiply both sides by 1 over 100 minus y. The dx is divided out over here. The 100 minus y is divided over here, and I end up with that. And once I'm there, I'm in pretty good shape. Okay? Y'all with me? All right. Integrate both sides. Be careful with the negative. All right? Since it's 100 minus y, du equals negative dy, so don't lose that negative. Okay? I have it here. Then I went ahead and moved it over to that other side because as we learned 2 days ago or yesterday, it kind of messes you up if that negative's in the way. All right, so we good from there? Any other questions on 10? All right. Here's what you need to work on today. Page 429, 1 through 21 odd. 45 and 47. I think it's fairly likely some of these problems are challenging.